Alright, so my last recording kind of froze. Well, I froze in it, and thus I have to redo this, at least from the point I stopped. So here we are, back at ignoring values in a pattern. Let's close this. You've seen that it's sometimes useful to ignore values in a pattern, such as in the last arm of a match, to get a catch-all that doesn't actually do anything, but does account for all remaining possible values. There are a few ways to ignore entire values or parts of values in a pattern, using the underscore pattern, which you've seen. Using the underscore pattern within another pattern, using a name that starts with an underscore, or using ... to ignore remaining parts of a value. Let's explore how and why to use each of these patterns. So yeah, this part of the section is pretty much a chain from everything above it. From here onward, it's just about ignoring things. And we start off with the full ignore, like ignoring an entire value with underscore, which we've seen and actually used. So continuing onward. Ignoring an entire value with underscore. We've used the underscore as a wildcard pattern that will match any value but not bind to a value. Although the underscore pattern is especially useful as the last arm in a match expression, we can use it in any pattern, including functional parameters, as shown in listing 18-17. So here, what they're showing is we have a function foo, right? We have an underscore instead of a value, and then we have the I32, and then we have y is I32, and then within the scope, we only use y. And main, here, we still pass in 3 and 4, we still pass in 2 values, but the first one, because it's associated with the underscore, is ignored completely. And there are a few reasons why you might want to do something like this. The one that came to the top of my mind is if you're refactoring old code and one of those parameters is no longer needed, but you don't want to change the API that the other parts of your code base expect, because then that could be a lot of changes just throughout. So this would be useful. You just change that one parameter that you no longer need to an underscore, and then continue as business as usual. At least that's what my thought was. So what did they say here? This code will completely ignore the value passed as the first argument, 3, and will print this code only uses the y parameter, 4. In most cases, when you no longer need a particular function parameter, you would change the signature so it doesn't include the unused parameter. Ignoring a function parameter can be especially useful in some cases. For example, when implementing a trait when you need a certain type signature, but the function body in your implementation doesn't need one of the parameters, the compiler will then not warn about unused function parameters, as it would if you used a name instead. So they pointed out 2 things here, right? One, that this is valid Rust code. You're not going to get a warning. You're not going to get any type of a compilation error. It's good. But another thing they pointed out, which is a more valid reason for this case even happening in the first place. So let's say you have a trait that has to adhere to a certain signature for reason X, but you don't need all the parameters that are given in that signature. In that case, you would definitely use something like this, just so you can adhere to the signature and then only place values with the parts of the parameters that you need, or the parameters that you need, and ignore the rest of them with underscore. So that makes sense. I can see that happening. Ignoring parts of a value with a nested underscore. We can also use underscore inside another pattern to ignore just part of a value. For example, when we want to test for only part of a value but have no use for the other parts in the corresponding code we want to run. Listing 18-18 shows code responsible for managing a settings value. The business requirements are that the user should not be allowed to override an existing customization of a setting, but can unset the setting and give it a value if it is currently unset. Okay, so let's see what they have here, right? Because they had a lot of words, but I want to see this code. So we have let mutable setting value equals sum5. So it has a value and it's sum. Okay. they have to let new setting value be something that is not mutable and sum 10. They have a match, and they have the matching against two values, so a tuple of 1 and 2. And in the first arm, they have sum underscore, which seemingly means that as long as there's a value in there, then this should match. As in, it's sum, but it's not a none. And that goes for both of them. So both of these have to have a value. And if they do, you get this. But if one of them doesn't have a value, then it's going to come down to this arm, which the underscore matches everything. And if it does do that, then the setting is going to switch. So this is something we can test out. Let's copy it over just to verify. All right, so I'm opening my editor. I can copy this in. Let me copy it again. Copy. Paste. Cargo format. Get rid of you. Cargo run. Now it looks all pretty. And we get setting is sum 5, which is here. This last line is the print statement. So you can see that this had a value, this had a value. So we skipped over here. Well, we got to this arm. We didn't skip over it. That should be right here. Yeah. We can't override because it has an existing value. However, if we change one of these, so let's change the new value to none. Run it again, see what happens. The setting is none. So what that means is we saw this arm, it didn't match, so it didn't print out this line. It went to this arm, which is the catch-all, and it set the setting value to the new value, which is none. And we can do the same thing the other way, which is sort of awkward, but it's possible. So we can make the setting value, the original one, none. I guess it's not awkward. It makes sense. You just want to change it. Now the setting value is sum 10. So yeah, that works seemingly as expected. Continuing onward. This code will print cannot override an existing customized value, and then setting is sum 5. In the first match arm, we don't need to match on or use the values inside either sum variant. But we do need the test for the case when setting value and new setting value are the sum variant. In that case, we print why we're not changing setting value and it doesn't get changed. In all other cases, if either setting value or new setting value are none, expressed by the underscore pattern in the second arm, we want to allow new setting value to become setting value, which we demonstrated by changing one or the other to none. We can also use underscores in multiple places within one pattern to ignore particular values. Listing 18-19 shows an example of ignoring the second and fourth values in a tuple of 5 items. Alright, so in this example, we have numbers, and we have a tuple of 5 items, at least that's what they said here. 2, 4, 8, 16, and 32. And then we match on numbers, which is the tuple. So the match right now has 5 items, and the second and fourth item are underscores. So yeah, we don't care about those. And we seemingly only have access to the first, third, and fifth. Those are the ones that get binded. So that makes sense. That's pretty straightforward. I'm going to skip over that. Oh, one thing to note is that, so we know that matching, right, has to be exhaustive, as in all possible values. Here we only have one arm. And the reason why we only have one arm is because we don't need a default case. This covers all cases. Because first is going to match to anything here. Third is going to match to anything here, and fifth is going to match to anything here. And so are these. These are going to, well, ignore anything in the other 2 places. So we only need one arm for all cases. This code will print some numbers 2, 8, 32, and the values 4 and 16 will be ignored. Ignoring an unsafe variable by starting its name with underscore. If you create a variable but don't use it anywhere, Rust will usually issue a warning because that could be a bug. But sometimes it's useful to create a variable you won't use yet, such as when you're prototyping or just starting a project. In this situation, you can tell Rust not to warn you about the unused variable by starting the name of the variable with an underscore. In listing 18-20, we create 2 unused variables, but when you run this code, we should only get a warning about one of them. And here is the code, and let's verify that. So we see that here X has an underscore in front of it and Y does not. So we should get a warning about Y but not about X. And here we go. Oh, they actually had a main in there too. I don't need a second main. And I don't need you. And let's see this warning. And here is the warning, unused variable Y. And there's nothing above it. Help, consider prefixing with an underscore. And they gave us an example. Okay, so that's a thing. And they stated there are plenty of reasons why to use this. When you're starting out a project, just prototyping, and you don't know if you're going to use all these variables or not, and kind of just don't want to get rid of that code. Yeah, it's understandable. Here, we get a warning about not using the variable Y, but we don't get a warning about not using the variable preceded by the underscore. Note that this is a subtle difference between using only underscore and using a name that starts with an underscore. The syntax underscore X still binds the value to the variable, whereas underscore doesn't bind at all. To show a case where this distinction matters, listing 18-21 will provide us with an error. Yes, this I do remember. So we have this scenario, right? We have some string from hello. This is going to be S. And then we have if let some underscore S equal S. This statement right here, if I recall correctly, moves S into the underscore S. And as such, you can no longer use S here because the value's already been moved. And that should be the error. But let's always verify. Let's verify. Format first, then verify. And here it is. Value moved here. Value borrowed here after partial. Is this a partial move? How do I scroll over? We'll receive an error because the S value will still be moved into underscore S, which prevents us from using S again. However, using the underscore by itself doesn't ever bind to the value. Listing 18-22 will compile without any errors because S doesn't get moved into underscore. And then, so what they changed here is that they removed the S here, and it's just an underscore. And here, this thing should run. See, no errors. However, it should be noted that even though this runs and works, this doesn't really make any sense. So as long as S exists, then you're going to print out this string. There are probably better ways of writing that. But yeah, this is just a case to exemplify the difference between underscore and underscore with the variable name after it. One binds to the value and the other one doesn't. This code works just fine because we never bind S to anything. It isn't moved. Ignoring remaining parts of a value with ... With values that have many parts, we can use the ... syntax to use only a few parts and ignore the rest, avoiding the need to list underscores for each ignored value. The underscore pattern ignores any parts of a value that we haven't explicitly matched in the rest of the pattern. In listing 18-23, we have a point struct that holds a coordinate in 3-dimensional space. In the match expression, we want to operate only on the x coordinate and ignore the values in the y and z fields. So let's look at this real quick. We have our struct point x, y, z, all I32. We have our origin, so let origin equal point and 0, 0, 0. Got it. And then we have our match expression. Match origin, which is that variable. And then we have point, we have the x value, which is seemingly the one we want to bind. And then we ignore the y and z. And then we could just write it like this instead of doing underscores for each of those, which is kind of nice. It's like a little shortcut. And let's just verify this. Put the point above main. Format. Bam. Looks nice and pretty. Now let's run it. X is 0. And to make this more interesting, we would just make x anything. So make it like 45. X is 45. Cool. So that worked as expected. That was pretty clear. We just used the dot dots to ignore the rest of the things in the fields. The x and z. Sorry, the y and z. X is not being ignored. We list the x value and then just include the dot dot pattern. This is quicker than having to list y colon underscore and z colon underscore, particularly when you're working with structs that have lots of fields in situations where only 1 or 2 fields are relevant. So yeah, they're just exemplifying why the dot 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 pattern is useful. So if we had a struct with a ton of different fields, let's say 10, and we only needed 1 of those, that's 9 underscores that we have to write. Just use a dot dot and you're good. You're golden. The syntax dot dot will expand to as many values as it needs to be. Listing 18-24 shows how to use dot dot with a tuple. Okay, so this is pretty similar. We have function main, numbers, same numbers before, 2, 4, 8, 16, 32. And looks like we have a match on the numbers, and we only care about the first one and the last one. So this is sort of exemplifying the fact that the dot dot expands for any amount of numbers in between. And right now we have 3 numbers in between that we're using the dot dot to ignore explicitly. So that makes sense. I'm not even gonna copy that one over and run it. That looks good. In this code, the first and last values are matched with first and last. The dot dot will match and ignore everything in the middle. However, using dot dot must be unambiguous. If it is unclear which values are intended for matching and which should be ignored, Rust will give us an error. Listing 18-25 shows an example of using dot dot ambiguously, so it will not compile. This one is interesting. So we have main, right? We have the same numbers as before. Now we have a dot dot in here, and we have a dot dot here. And then we have the second. So the reason why this is ambiguous, right, is because second is meaningless to Rust. This is just a variable name. It binds to it. It could be third, fourth, fifth, x, y, z. It could be anything. And because of that, we know that this is dot dot. It's going to expand to unknown amount, and this is going to expand to unknown amount. For example, this could be 1, just cover the 2. This could be the second value, 4, and this could be the 8, 16, and 32. Or this could easily be the 2 and the 4. This could be 8, and then this could be the 16 and 32. There are other patterns as well. But yeah, just keep that in mind. 2 dot dots in one pattern, that's kind of a no-no. Oh, the error. That's right. We have an error. Let's see what the error is. We no longer need this point. And we're right here. And looks like I have an error. Did I forget to copy something over? Here to here. Oh, that looked right. Well, let's see what you say. They noted the error. It states here, make this a little bigger. The dot dot can only be used once per tuple pattern. And for obvious reasons, we already stated. And it notes where we used it prior. So right here. And is that the same error they have? The wording's slightly different, but yeah. Error dot dot can only be used once per tuple or tuple struct pattern. Yeah. Okay. Moving onward. It is impossible for Rust to determine how many values in the tuple to ignore before matching a value with second, and then how many further values to ignore thereafter. This code can mean that we want to ignore 2 and bind second to 4, and then ignore 8, 16, and 32. Or that we want to ignore 2 and 4, bind second to 8, and then ignore 16 and 32, and so forth. The variable name second doesn't mean anything special to Rust, so we get a compile error because using dot dot in 2 places like this is ambiguous. Which, yeah, I stated earlier. Alright, extra conditionals with match guards. Now, if you recall correctly, match guards was mentioned at the very top of this document, saying that's something we will get to later. We're finally here. A match guard is an additional if condition specified after the pattern in a match arm that must also match, along with the pattern matching for that arm to be chosen. Match guards are useful for expressing more complex ideas than a pattern alone allows. The condition can use variables created in the pattern. Listing 18-26 shows a match where the first arm has the pattern SUMX and also has a match guard of if x less than 5. Alright, so based on what they stated here, this sounds like there's just a match with a conditional statement afterwards. And looking at the code that they have down here, we have let num equal sum4, match num SUMX if x is less than 5. So this is the match guard right here, which is just a conditional statement for x, given that x exists. And it should exist because it's sum. It matches to this thing. And then if x is less than 5, we print out this. And then if x exists and it's greater than 5, seemingly, then we print this out. And if it's none, we do this. So this we can test out, and this looks super useful. Super useful. Format. Oh, there we go. And then run. Less than 5, 4. And let's change num to 7. Run it again. And that got to this arm. Which, I mean, it came here, saw that SUMX was true, but the conditional statement, the match guard, was false. So it moved on to the next arm, which was this one, and it matched. And for giggles, let's do the none case. And let num equal none. I get an error about inferring things, which I did see before. I'm gonna ignore that for now, because I don't think I solved it last time either. Just one of the things I just don't know. Alright, so moving onward. This example will print less than 5, 4. When num is compared to the pattern in the first arm, it matches because sum4 matches SUMX. Then the match guard checks whether the value in x is less than 5. And because it is, the first arm is selected. Yeah. If num had been sum 10 instead, the match guard in the first arm would have been false because 10 is not less than 5. Rust would then go on to the second arm, which would match because the second arm doesn't have a match guard and therefore matches any sum variant, which we also saw. We didn't use 10, we used 7, but yeah. There is no way to express the if x less than 5 condition within a pattern. So the match guard gives us the ability to express this logic. In listing 18-11, we mentioned that we could use match guard to solve our pattern shadowing problem. Recall that a new variable was created inside the pattern in the match expression instead of using the variable outside the match. The new variable meant we couldn't test against the value of the outer variable. Listing 18-27 shows how we can use a match guard to fix this problem. And again, they're alluding to, at the top of the document, 11, because we're now at 18-27, so a while back, but still this document. And the code looks familiar. We have x, some 5, y, and then here is where looks like they added the guard. So let's start from the top of the match, right? We're matching against x. We see x, some 50, print line, we got 50. Okay, this is explicitly matching against the value of x. And then here we have the n, which is the value that we're going to match against. But we do if n is equal to y. So here's y, and we're matching against y. And then here we use the shadowed variable of the n, because it's still being created. But we now know that n is going to explicitly be the same value as y, because we have the equivalency there. So you know that n is going to be, if n is 10, sorry, we know that if x is 10, then this should match. And then we have the default cases. So let's just verify that real quick. Copy. Print out. So currently we have x is equal to 5, right? So it doesn't match this one because x is not 50. It doesn't match this one because n is not equal to y. Y is 10. N is going to be 5 in this case. And then it moves on to the default case, which it states right here. But if we move this to 10, we should catch the match arm. And here we have a match, n equals 10. So because this matched, we hit this arm. And what this allowed us to do was match x against an outer variable y, which is something we couldn't really do last time. And just so I can see the first arm, just curious. Bam, got 50. All right, moving on. This code will now print default case x equals sum 5. The pattern in the second arm doesn't introduce a new variable y that would shadow the outer y, meaning we can use the outer y in the match guard. Instead of specifying the pattern as sum y, which would have shadowed the outer y, we specify sum n. This creates a new variable n that doesn't shadow anything because there is no n variable outside the match. And again, it created n, but allowed n to be compared against the original y, and that's why it's useful. The match guard if n equals y is not a pattern, and therefore doesn't introduce new variables. This y is the outer y rather than a new shadowed y, and we can look for a value that has the same value as the outer y by comparing n to y, which is what we did. You can also use the OR operator pipe in a match guard to specify multiple patterns. The match guard condition will apply to all the patterns. Listing 18-28 shows the precedence of combining a match guard with a pattern that uses pipe or OR. The important part of this example is that the if y match guard applies to 4, 5, and 6, even though it might look like if y only applies to 6. All right, so let's look at this thing down here. So we have let x equal 4, let y equal false, and then we have this match thing. And what they're stating is that this is one condition, but this is the guard, and this guard applies to 4, 5, and 6, even though it kind of looks like 6 if y. It kind of looks like this is the thing, but as you can see down here, it's more like this than this. In any case, let's verify this. Format, run. So we printed no. Oh, because y is false. Let's make y true. And let's show that it works for all of 4, 5, and 6. So we print out yes for 4, verify for 5, and let's verify for 6. So as we noted, like the first time we ran it, when y was false, because the conditional was false, this did not match, and we went to the default case, which is print no. But outside of that, when we put y to true and then we tried 4, 5, and 6, all of those came out and matched to this arm and printed out yes. So we make this 7, which is outside of the scope of 4, 5, and 6, we should get a no. And we get a no. All right, moving onward. The match condition states that the arm only matches if the value of x is equal to 4, 5, or 6, and if y is true. When this code runs, the pattern of the first arm matches because x is 4, but the match guard if y is false, so the first arm is not chosen. The code moves on to the second arm, which does match, and this program prints no. The reason is that the if condition applies to the whole pattern for pipe 5, pipe 6, not only to the last value 6. In other words, the precedence of a match guard in relation to a pattern behaves like this. And I alluded to this earlier, but here is the first condition, 4, 5, or 6, and here's the second condition, if y. Rather than this thing, which is 4, 5, or 6 if y, which is kind of just separated. After running the code, the precedence behavior is evident. If the match guard were applied only to the final value in the list of values specified using the OR operator, the arm would have matched and the program would have printed yes. So what they're stating here is that if this condition was true, if this is how it worked, then we would have saw the 4. The y, even though the y was false, we still would have printed yes because we would have matched solely on the 4. But that's not how it ran. So yeah, back to this is how it looks like in actuality. At bindings. The at operator, at, lets us create a variable that holds a value at the same time we're testing that value to see whether it matches a pattern. Listing 18-29 shows an example where we want to test that a message hello ID field is within the range 3 to 7. But we also want to bind the value to the variable ID variable so we can use it in the code associated with the arm. We could name this variable ID the same as the field, but for this example, we'll use a different name. So seemingly this allows us to grab hold of the value within the match, especially when we're using ranges. So let's look at the code real quick. You have enum message, you have a variant, hello, comes with an ID. So let message equal message hello ID 5. And then here's our match. We have a match on message. We have the variant of hello for the enum right here. And then we have ID, and then we have the variable name, which in this case is going to be ID variable, ID underscore variable, at. So this does the binding. And then we have the range condition, which is 3 to 7. So if something was in this range, then the value should be bounded to ID underscore variable, and then we can use it within this scope right here. And then they have the second arm, which is a different example. It doesn't have the at symbol, but we do have a range. And it says we just found the ID. It seemingly does not have access to the actual number that the ID is associated with. And then we have the last case, which just binds to everything because it doesn't have a range, no specification, just prints out something. And it prints out the ID. So yeah, the difference between this one and the first arm and the third arm, the last arm, is this will always match to any ID, but this one allows, the first one allows for a conditional. So let's print this out just to see it in work. Put that here, and let's move the enum out. Delete. Put the enum at the top. Format this, make it look pretty. Ooh, cleans up nice. And then run it. So here we have ID 5. ID 5 is within the range of 3 to 7. And they even made it look pretty. Like they broke it up into another line, which they didn't do here. Back to the ID. IDE. So they did hello, put a new line there, new line here for this arm, and then here's the scope for afterwards. Anyway, because 5 is within the range of 3 to 7, we got to here, and ID underscore variable bounded to the 5, and we were able to print it. That's why we were able to see it here. So if we do range, let's do 11 to get to the second arm. Found an ID in another range, and that's this range. But if we wanted to just to print the ID, then the last arm is best. And to get there, we just need something outside of the range of 3 to 7 and outside of the range of 10 to 12. 8 kind of falls in between. Let's fall in between the cracks. Found some other ID 8, which, as you can see, is the last arm. Alrighty. This example will print found an ID in range 5 by specifying ID underscore variable at before the range 3 to 7. We're capturing whatever value matched the range while also testing that the value matched the range pattern. In the second arm, where we only have a range specified in the pattern, the code associated with the arm doesn't have a variable that contains the actual value of the ID field. The ID field's value could have been 10, 11, or 12, but the code that goes with the pattern doesn't know which it is. The pattern code isn't able to use the value from the ID field because we haven't saved the ID value in a variable. In the last arm, we specified a variable without a range. We do have the value available to use in the arm's code in a variable named ID. The reason is that we've used the struct field shorthand syntax, but we haven't applied any tests to the value in the ID field in this arm, as we did with the first two arms. Any value would match this pattern. Using at lets us test a value and save it as a variable within one pattern. That seems very useful. I'm not sure why they waited till the end of chapter 18 to tell us about this, but that seemed very useful. Thank you for sharing it with us. And then the summary. Rust patterns are very useful in that they help distinguish between different kinds of data. When used in match expressions, Rust ensures your pattern covers every possible value or your program won't compile. Patterns and let statements and function parameters make those constructs more useful, enabling and destructuring of values into smaller parts at the same time as assigning to variables. We can create simple or complex patterns to suit our needs. Next, for the penultimate chapter of the book, we'll look at some advanced aspects of a variety of Rust features. And yeah, that's the end of chapter 18. Only 2 chapters left, 19 and 20, and then we are done. We are done. If you like the video, hit like, subscribe. Outside of that, see you next time. Peace.